or the chopper circuit. So a chopper circuit or a DC-DC converter is mainly used to convert a fixed DC into variable DC, and we need this variable DC in order to control the speed of the DC machines. So speed control of DC machine is one of the most important application of DC-DC converter, right? So there are many other technologies by which we can obtain the variable DC by using power semiconductor devices or by using power converters, but chopper circuits are the most suitable type of converters because it's using only a fixed DC source voltage. Only a fixed DC source voltage like a battery cell is required here as the source voltage. So this is the basic block diagram of DC-DC converter or chopper circuit containing a switch which is nothing but a semiconductor switch. It can be thyristor, it can be IGBT, it can be a MOSFET. So these thyristors, IGBT, MOSFETs, these are all semiconductor switches which are having third terminal called a gate terminal, which is not available in diode because diode is called uncontrolled semiconductor device, which is diode is also a semiconductor device, but in diode the gate terminal is not available. So for the semiconductor devices like the thyristors, IGBT, MOSFETs, a new feature is there that their gate terminals can be controlled, and by controlling their gate terminal by sending suitable gate signals or pulse signals, we can vary the output DC voltage of the chopper circuits by using these two methods. One is called the pulse width modulation method and second is called the pulse frequency modulation. In first case, we'll vary the on time period. T on is the time period for which your switch will be kept on. Okay, because this semiconductor switch present in this chopper circuit must be turned on and off very rapidly. That means here at the gate terminal, whatever signal is required to send must be having very high frequency, very high switching frequency. This frequency is called as switching frequency. So switching frequency of the getting signal must be very high in order to turn on and off the switch present in this chopper circuit so that we can control the output DC voltage smoothly. And the second method is here in the first case, the frequency, the time period will be kept constant, will vary only the on time period. And we have learned one new factor here in power converter called as small d, the duty ratio. Okay, this is the graphical response of duty ratio versus the output DC voltage V naught. V naught is the average DC output voltage of the chopper circuit. Okay, so this duty ratio is the ratio of T on the on time period divided by the total time period. Fine. So in case of pulse frequency modulation technique, we'll vary the frequency, keeping the on time period same. Look at these graphs, the on time periods are same. We are changing only the frequency or the time period. So either by varying the on time period or by varying the time period of frequency, in other words, we can vary duty ratio, and by varying the duty ratio, we'll be able to calculate, we'll be able to vary the DC output voltage. So there are there are many types of DC-DC converter circuits, but two major types are buck chopper and the boost chopper. So let us start with step down chopper circuit or buck converter circuit. The figure 1 is representing, this one is representing the circuit diagram of basic step down chopper circuit. This is one basic topology of chopper circuit. There are many more topologies of buck converters available. So as you can see here, only one number of semiconductor switch is required, this S, along with the input voltage source, which is a DC, fixed DC, that means a battery. This is the diode. This is inductor and this is resistor. Okay, this RL, these two are basically the load of the circuit. Suppose by using this converter circuit, you would like to um, blow a bulb, or you want to use a bulb as a load here. Fine. So RL is the load here, and there is a specific purpose of this diode. I naught is the load current, I is the source current, VD is the voltage drop across the diode, and ID is the current through the diode. V naught is the output DC voltage, average DC output voltage. So here both VI and V naught are DC, but since it's a step down chopper, that means definitely V naught will be lesser than VI, the input voltage. Okay, so first you consider the second figure showing the equivalent circuit for on state. For on state means when the switch is closed. The switching on and off will be done by the control circuit, by the triggering signal. So when the switch is closed, what will happen? The circuit will be closed and the current II will be flowing through this circuit, right? And this diode will be reversed biased, because whenever this switch is closed, what will happen? Current starts flowing through this path, right? Because the cathode of the diode is connected with this, right? So definitely there is a positive voltage across this, and we know that diode will only operate whenever anode is made positive with respect to the cathode. So this time, when switch is closed, diode is reverse biased. So if diode is reverse biased, since it's a unidirectional unilateral element, no current will flow from cathode to anode. So the entire current will pass through the load circuit. So definitely ID is 0. Diode current is 0. No current will be flowing through this. Right? So this this branch will be left open. But though the two terminals are left open over here, there must be a voltage, open circuit voltage across these open circuited uh, terminals. Open circuit doesn't mean that the voltage is 0. There is definitely a finite voltage, and here in this case, this voltage is nothing but the source voltage. The entire voltage will be developed across this open circuit at steady state. So now current will be flowing through this load. It's an inductive load, so inductor will be storing some energy because it's an energy storing element. So whenever current is passing, that means whenever current is rising through this inductor, the voltage will be developed. That means during the transient period, as soon as you close the switch, what will happen? Current starts rising. Currents will start rising from 0 ampere to say the final steady value, that is, for example, consider I ampere. So whenever there is a rate of change of this I, the voltage will be developed across the inductor. And since it's a DC circuit, when the input current will reach its steady state, that means the constant value of current, say for example I ampere, there will be no change of current present in the circuit. So voltage developed across the inductor will be 0. But till then, there is a rate of change of current up to during this transient period, and voltage will be developed across this load. So there will be some voltage V naught. So this is case 1, when the switch is closed. Now automatically after some time, the switch will be left open. Okay, depending upon the control strategy or control circuit that we have designed initially for the gate terminal of this semiconductor switch, right? So as per the getting signal that I have shown earlier, this type of getting signal is required to send at the gate terminal of the switch present in the buck converter. Okay, so whenever the switch is open, that is this period T off, the period T off, for this period, for this small period, what happens actually? the circuit means supply voltage is disconnected from the load side. The source is disconnected now because the switch is opened. And what happens now? Supply is disconnected, no source current is flowing, but that means inductor is now carrying some energy within it, right? So now since the supply is disconnected, what inductor will try? Inductor will try to dissipate its stored energy through some other path, right? And in order to implement that thing, definitely the polarity across the inductor must be reversed because V is equals to L didt, or we'll apply here the Lenge's law, which is showing that the voltage developed is just opposing the cause of it, which is the current, right? So here definitely the voltage across inductor will be reversed. So previously this is at positive polarity, now this is at negative polarity. And we all know that current through inductor cannot change instantaneously. It takes some time to dissipate its energy. And it requires a path, a freewheeling path. So here this diode will be acted like a freewheeling diode. You can see this is now positive, so current will start flowing from this terminal through R and then via this diode. So now this time the diode the anode of this diode is made positive. Look at this polarity, it's positive. So current is flowing like this in the upward direction, right? So definitely the diode will be forward biased. That means anode of the diode will be made positive with respect to cathode. So current will be flowing through the diode. And when it is conducting, when the diode is conducting, definitely if you consider ideal diode, there will be no voltage drop across the diode. So this part will be like short circuited, this part containing the diode. Whenever diode is conducting, if it's ideal diode, then definitely it will be a short circuited part. Right? The voltage drop across the diode during the conduction mode of the diode will be equals to zero. So zero voltage means the short circuit part. So current will be flowing. Whatever energy is stored within the inductor, that will be totally dissipated through this path. And again, after some time, the switch will be closed, and again current will be rising through the inductor. So this time again the voltage will be developing across the inductor, and but this diode will be left open. It will be not conducting because it's now reverse biased, and this process will continue. We will be getting this type of voltage across the load. When the switch is closed, a positive voltage. When the switch is closed, open, a zero voltage. Now, is zero voltage, see, this path is left short circuited when the switch is open, and the short circuited path is connected in parallel with the load. So what is the voltage across the load? It's just zero. So this is the working principle of basic step-down chopper circuit. Now if you have any questions, please ask me. Now next, coming to the waveform analysis of a buck converter for the continuous current mode. What is meant by this continuous current mode? Current is flowing continuously. There is no discontinuity, right? So here the current mode can be of two types. One is called the continuous current mode, and one is called the discontinuous current mode. Okay, just look at the current signal, the output current signal. Here in this case, for continuous current mode, output current is continuously flowing, right? And in case of discontinuous current mode, look at the current output current waveform. The current waveform touches the zero, the x-axis, at this instant. Okay, so here a discontinuity occurs. But in case of continuous current mode, current is not touching the zero axis. It is continuously flowing through the circuit. So These are the two modes, two current modes uh, we can consider for buck converter as well as for boost converter depending upon the control strategy, control circuit for the triggering signal. Okay. Now, as I told you earlier, the DC-DC converter, DC-DC chopper circuit is just like a transformer, whereas transformer is AC to AC converter. That means here the volt current relationship at the input side will be exactly equal, identical with the voltage current relationship at the output side. Right. That means product of the average value of voltage and current at the output side will be just equal to the average voltage current at the input side. That means P0 is equals to Pi. The power DC power drawn from the source must be identical with the DC power absorbed by the load. Hmm. So here voltage can be either stepped up or stepped down, just like transformer. But the power drawn from the source cannot be amplified, cannot be changed at the load side. So P0 must be equals to Pi. So from this, we can simplify the expression of output current as II by D. Previously, we have seen the expression of output voltage V0 equals to D times Vi. This is the expression of output voltage for buck converter. And this is the expression of current, output current for buck converter. So it's inversely proportional with D, the duty ratio. So first one is showing the input voltage curve. You can see, and this dotted line is showing the average DC output voltage. This is the diode current. So definitely when switch is closed for the on-time period, it's not working. We have seen there is no ID, no diode current, but when it is conducting, for the second case, when the switch is open, the diode is conducting, there is definitely a diode current. So this is the diode current ID for the off-time period of the switch. This is source current. So definitely for the on-time period, the source current will be available. And look at the graph, look at the response. Uh, Here, the current II is basically rising, right? The peak is, the top of this graph during this period, it's not flat. It is rising. Why? Because current is rising and current becomes steady after some time. So current is rising from this position to this during the on-time period. Okay, look at the output current waveform. It is just a triangular waveform because current is rising for the time period when the switch is closed and it is decaying. See the output current, look at the output current, look at the diode current, it is decaying in nature for the time period T off because this time current is decaying through the freewheeling diode because the supply is disconnected. There is no source current. And look at the graph. Source current is zero. That means supply is disconnected. The switch is open, but still there is some current due to the inductance present in the circuit. That current will be flowing through the diode and obviously through the load. So diode current is available and it is see decaying curve. It should be an exponential decaying curve, and also in I naught in the response curve of I naught, the current is decaying for this time period. And last waveform is the voltage across inductor. Voltage is positive across the inductor whenever the switch is closed, and it is why? Because it has changed its polarity for the off time period of the switch. Okay. Similarly, for discontinuous current conduction mode, we'll get this type of waveforms from buck converter. That means whenever the switch is closed, whenever the switch is on, we'll get the on-time period, we'll get this portion of the output current, and whenever the switch is off, definitely the diode must be on, the diode must be conducting, which is nothing but a freewheeling diode through which the stored energy within the inductor will be passing. Any questions up to this? Now look at the mathematical expressions carefully. When the switch is turned on, that means when the switch is closed, here I have taken, for this mathematical analysis, I have taken only the resistive load. Right? I have taken resistive load only. So, when the switch is closed, what will happen? Voltage will be developed across this inductor. Look at the polarity carefully. This side is positive. So, voltage developed will be L di dt. And from this, we will calculate IL as 1 by L integral PL dt. Right? And when the switch is turned off, that means when the switch is opened, what will happen? Voltage drop across the inductor is just equals to minus of V0, because the polarity of voltage across the inductor is changed, is reversed. So here V0 is equals to minus V0, and you can obtain this equation from the KVL equation of this bigger loop, because now the switch is open, so voltage source, the input source is disconnected. So this is the loop only you have. So considering this, you will get that V0 is equals to minus of VL, or VL is equals to minus of V0. So mathematically, we can derive this for the buck converter, that output average DC voltage is equals to D times VD. This D is the duty ratio. So it can be either denoted by capital D or small d. So look at the graph. Here, when the switch is closed, what I have taken, the current is rising. This current is rising. Okay. So VL is VD minus V0. What is VD? VD is the input source voltage, right? And what is V0? The load voltage, average load voltage. So when the switch is closed, definitely VD minus V0 is equals to VL. Okay. And also, we can write this from this equation, ddt of IL equals to VD minus V0 by L. Right? Now this ddt of IL can be obtained when switch is closed, and this will be the expression. Follow my cursor. This will be the expression del IL when the switch is closed is equals to VD minus V0 by L into D times T. What is dt? Capital D times T. What is dt? What is D? What is D?
Duty ratio.
Duty ratio. What is the expression of D? What is the expression of T? T on by T. T on by T, right? So T on can be expressed as D times T. T is the time, total time period, right? So here in this expression, what is this dt? The time period for which the current is rising, that means when the switch is closed, that means dt is the on time period. So this on time period can be expressed as capital D times capital T. Okay, and when the switch is opened, remember this expression, the current del IL when the switch is closed. Del IL means the difference in current from this instant, 0 instant, to this maximum instant. And similarly, we'll obtain del IL for the off time period of the switch. That means when the switch is open, del IL open for this duration, dt to t, when current is decaying in nature. So this time dt means t off, and this t off can be calculated as 1 minus t into t, because t on plus t off is equals to total t. That means T on is just T minus T off, and T on means T times T. So it can be further represented as 1 minus T times T. Fine. and VL is minus V naught. When the switch is opened, VL is minus V naught. The load voltage is just exactly equal and opposite to the load voltage developed across the load, and VL is LDIDT. So from this we can calculate del IL. The switch is opened as minus V naught by L into 1 minus D into T. Okay, and if you combine these two current, that means this current and this current, what should you get? You should get 0. Why? Because whatever current is using in order to store some energy within the inductor, that must be totally dissipated through some path, right? That means whatever energy was stored within the inductor, that must be released during the off time period of the switch. So the total current, the on time current and the off time current increment must be equals to 0. So del IL closed plus del IL open must be equals to 0. So you just put the expression of del IL closed, this one, and del IL open, this one. Over here you will get, and if you equate these two currents equals to 0, you will get V0 equals to D times VD. That means average DC output voltage for buck converter is equals to duty ratio times the input voltage. That means if the input voltage of the DC-DC converter circuit is 100 volt, and if the duty ratio is 80%, then what should be the value of the average DC output voltage? It should be only 80 volt. 80% into 100, 80%. Hence 0.8 into 100. Okay, so it is just 80 volt. That means by using buck converter or step down chopper circuit, the input DC voltage, the fixed input DC voltage can be converted to variable DC output voltage, in which the average DC output voltage will be just equals to 80% of input voltage, that is 80 volt. Look at the expression of output voltage, graphical response of output voltage. It's a pulsed signal. The dotted line is showing just the average value, right? But if you want to measure the RMS value of the output voltage of buck converter, how do you calculate the RMS voltage? The solid line is showing the actual output voltage response curve of buck converter. It's just a pulse signal. So just apply the fundamental formula, square root 1 by t integral 0 to t v square dt. Here v means the output voltage, so we'll consider v0 square, right? And 0 to t, t means the total time period. So total time period is actually here k times t. The k is just a duty ratio, right? So total time means here the on time period. So on time period means t on, which can be represented as d times t. So here in this derivation, I have taken k as duty ratio. So k times t. To simplify this integration, you will get V naught. The RMS value of the output voltage of buck converter is equals to square root of duty ratio multiplied by the input DC voltage, which is Vs. Because the output voltage for the on-time period of the switch is just equal to Vs. We can calculate this from the graphical representations of DC-DC converter circuit, step down type. See? V0 is just equal to Vi for the on-time period of the switch. Okay, so here we'll put V0 equals to Vs in order to calculate RMS value of the output voltage. Is it clear to everyone? Okay, next I'll skip this derivation. It's not required for your curriculum, so I'll skip this. This is the derivation showing this ripple current. Look at this current signal, this ripple current. IL max minus IL min. How to calculate this difference, del IL? This is called the ripple. This is the graphical representation of inductor current. right? Inductor current. It's a DC circuit, so definitely it should be a constant line, right? Current should be constant across the load because it's a DC circuit. Here the constant current is desirable, but instead of getting constant DC current, what we are getting actually, we are getting this type of triangular shaped current. Look at this output current signal, we are getting actually the triangular shaped current signal. And this dotted line is showing the average current value, which is II by T, right? So we need to connect a suitable filter circuit across the load in order to reduce this ripple. But before that, we need to detect how much ripple is present in the circuit. Now, for the detection of this ripple current, we need to uh, consider this derivation, mathematical derivation, to find this I max and I min. Finally, by using this relationship, we can calculate the ripple current, the peak-to-peak ripple current of buck converter. Next, we'll see boost chopper or step up DC-DC converter circuit. Definitely here we'll obtain output DC voltage higher than the input fixed DC voltage. And this is the topology of the basic step up chopper circuit. There are many other configurations of step up chopper circuits. Here the switch S is a semiconductor switch. So case 1, the on state means when the switch is closed. Look at the circuit diagram. Only this path will be closed, and diode anode is made negative now, depending upon the circuit configuration. So it will be reversed biased. No current will be flowing through this path. That means these two terminals will be left open because it is not conducting. The diode is not conducting. And for the off state, what is happening? The switch is opened. The switch is opened. That means these two terminals are left open. That means the entire current is flowing through this path. So this path, and this time diode is forward biased. Why? Because this time this anode is made positive. Why? Because during this case, when the switch is open, inductor will try to dissipate its energy. So inductor will change its voltage polarity. That means now the polarity is made positive at this terminal across the inductor, which in turn makes the diode forward biased. Okay, so this time diode current is present in the circuit, diode is conducting, so voltage drop across the diode is 0, so it will be at like a short circuited path. So this time current, the source current II is flowing through this path. Okay, so here a resistive load is taken, R load. V0 is the average DC output voltage across the load. I0 is the load current. II is the source current. So we'll apply the same mathematical equation in case of boost converter. Now this time VL, what is VL? The inductive voltage is just equals to VD. What is VD? The source voltage. Look at the circuit. This side is left disconnected from the input side. So you just apply KVL, what you will get? You will get VD equals to VL. Why? Because when the switch is conducting, ideally there is no voltage drop across the switch. Right? If you consider ideal switch, when it is conducting, the voltage drop across that switch should be equals to 0. So if you apply KVL here, you will get only VD equals to VL. What is VL? It's just LDIDT. Or LDILDT. We consider this current is IL because it's passing through the inductor, right? And what is this dt? The denominator of this didt. This dt is nothing but del t. What is this del t? The time period for which the switch is closed. That means dt. D is the duration, dt. So didt is Vd by L. That means del IL closed is Vd dt by L. Current is rising. The inductor current is rising. And it is maximum exactly at the instant dt, because after which the switch is left open. Fine. So VL is equals to VD when the switch is closed. But when the switch is opened, what is VL? It is VD minus V0. which is Vd minus V0. Look at the circuit diagram, equivalent circuit diagram. When the switch is opened, this switch is opened. The inductor has changed its polarity. Why? Because this time inductor is trying to dissipate its stored energy, right? So this is now positive. Previously, this side was negative polarity. This side. Look at the circuit. This side was negative, but now this side will be positive. So since it's now positive, current will be flowing like this. So anode of the diode will be now positive. So diode will be forward pass. So current will be flowing like this through the load circuit. Okay. And here this capacitor, for both these two cases, buck converter and boost converter, this capacitor is just like a filter. We have connected it in parallel with the resistor in order to reduce the current present in the load current waveform. Fine. So definitely this source current will be passing through this capacitor. Whenever the switch was closed, this side is open, so no current is flowing through this and this. But definitely whenever the switch is open, current is flowing through the capacitor. So capacitor is getting charged, and at the steady state, definitely this capacitor will be charged with this full input voltage Vd. Fine. So look at the mathematical derivation. This time VL is equals to Vd minus V0. How to obtain this? So just consider this figure look for the KVL equation, which is Vd equals to VL plus V naught. Vd. Now this time source voltage is just summation of the load voltage V naught and this inductor voltage. Is it clear to everyone? Don't follow this polarity across the inductor, because this time inductor polarity has changed. So this is now positive. So considering this side positive, anode side of diode as positive, you write down the KVL, you will get Vd minus V0 equals to VL. So again, we will calculate di dt. This dt is the off time period, which is 1 minus d times t. Fine. And by simplifying this, we'll get del IL open equals to this. So again, the del IL, the current value when the switch is closed is just equals to the current value when the switch is opened, right? So equating this summation with 0, we will get V0 equals to this Vd by 1 minus d. Vd is the source voltage, V0 is the average DC output voltage for boost chopper, and capital T is the duty ratio. Right? Now, if you consider 100 voltage as the input volt and 80% duty ratio, what will get? 100 by 1 minus 0.8. The denominator is 0.2. 100 by 0.2, how much? 200. That means boost converter produces output voltage which is greater than the input voltage. Right? And duty ratio value lies between 0 and 1. It cannot be higher than 1. Okay? Have any questions? Everyone understood the basic working principle, operation of boost chopper and buck chopper, and the mathematical derivations?
Yes, ma'am.
Okay. So this slide is showing the comparison between the on state and off state of the boost chopper. That we have already discussed. Next, the methods of controlling the gate signal of the semiconductor switch. That means the control circuit, because this control circuit design is very, very important for chopper circuit. based on the control circuit, based on the switching frequency and the modes of variation of the duty ratio, which is responsible for the variation of the output voltage. So here, the switching circuit or the control circuit is very, very important to understand. So basically, we use pulse width modulation control or constant frequency operation. In pulse width modulation control, the frequency is kept constant. So generally, we avoid the variable frequency control, as I told you earlier. Frequency variation is not a easy task, right? So in pulse width modulation, as we have seen already, we only vary the pulse width of the on-time period. That means this time period, keeping the total time period fixed. So actually, in practice, what we do in order to obtain this variable DC output voltage, we just take a comparator which will compare the desired output voltage and the actual output voltage from the chopper circuit, right? And the difference between these two will create the V control, which is definitely a DC signal. So just follow this, either this dotted line, V control 1, or this solid line, straight line, V control 2, right? Which will be further compared by a sawtooth waveform, this waveform, at the second input terminal of this second comparator. So this is the sawtooth signal, which is also called as the carrier signal, right? We'll consider a very, very high switching frequency. Next, we'll set a logic that whenever V control is higher than, here in this slide we have used, when the DC control, the V control is higher than the sawtooth, a pulse will be created. If you consider this V control 2, you will get this width. If you control V control 1, you will get this. So you can see that by changing the V control magnitude, which will be coming from these two values, we can vary the on-time period of the switch. And by varying the on-time period of the switch, keeping frequency constant, we can vary the duty ratio. And by varying the duty ratio further, we can vary the output DC voltage of the chopper, right? So here the switching frequency, the frequency of this carrier signal or the sawtooth signal must be very, very high, which is to be compared with a constant signal that will be coming from the desired DC and the actual DC, and the output of the comparator will generate the switch control signal. Is it clear to everyone? Okay. Fine. So next we have DC to AC converter. But next day I'll be starting that part. Right. So this is the end of DC-DC converter. Only these two converter circuits you have. So based on this, we'll solve a problem as given in this slide. The chopper circuit is operating on TRC. TRC means pulse width modulation control or time ratio control, TRC, at a frequency of 2 kilohertz on a 460 volt supply. If the load voltage is 350, calculate the conduction period of the thyristor in each cycle. Okay. So 2 kilohertz is actually the switching frequency, means the frequency of this carrier signal. Okay. VDC is 350 volt, that means input DC voltage, and output DC voltage is given, that is 460 volt. Okay. So chopping period means the time period with the switching frequency 2 kilohertz can be calculated as 0.5 millisecond. And we know the expression of VDC average for buck converts. It's what type of converter it is? Load voltage is 350. Load voltage is 350, okay? And source is 460 is VS. So VS is lesser than VT, V out. So it's a step down chopper, buck converter. So output voltage is simply D times P. So D can be calculated as T on by T. This is T. So you can calculate T on as 0.38 milliseconds. Okay, from this expression, because all the parameters are known except T on. So T on can be calculated as 0.38 millisecond. Is it clear to everyone?
Yes, ma'am.
Okay. So if you have any doubts, any questions, you can ask me.
No, it's clear.
Yes, who is this?
No, I'm saying it's clear.
Okay, very good. So now I'll be taking your attendance. Roll 1,
Present, ma'am.
2,
Present, ma'am.
3,
Present, ma'am.
4,
Present, ma'am.
5, Aditya Banerjee, 6,
Present, ma'am.
7,
Present, ma'am.
8,
Present, ma'am.
9,
Present, ma'am.
10,
Present, ma'am.
11, 12, Satyam, 13,
Present, ma'am.
14,
Present, ma'am.
15,
Present, ma'am.
16,
Yes, ma'am.
17,
Yes, ma'am.
18,
Present, yes, ma'am.
19, Chandrani,
Present.
okay, 20,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Yes, ma'am.
24,
Present, ma'am.
25,
Present, ma'am.
26,
Present, ma'am.
27,
Present, ma'am.
28,
Present, ma'am.
29,
Yes, ma'am.
30, 31,
Yes, ma'am.
32,
Present, ma'am.
33,
Present, ma'am.
34,
Present, ma'am.
35,
Yes, ma'am.
6,
Present, ma'am.
37,
Present, ma'am.
38,
Present, ma'am.
39,
Present, ma'am.
40,
Present, ma'am.
41,
Present, ma'am.
42,
Present, ma'am.
43,
Present, ma'am.
44,
Present, ma'am.
45,
Present, ma'am.
46, 47,
Present, ma'am.
48,
Present, ma'am.
49,
Present, ma'am.
50,
Yes, ma'am.
51, 52,